All right, well, again, good afternoon, everybody. I'd like to welcome you all to today's webinar. Today's topic will be asphalt pavement design for local agencies. Before we get started, I wanted to touch on the webinar controls that you should see here on your screen. As of this moment, all attendees are in listen-only mode, so you're all muted at this time. The questions pod, which you see highlighted should be towards the top right of your screen. This is where you'll type any questions or comments that you have. Feel free to use this at any time, and we'll have several points during the presentation where we will stop to address those questions. Finally, under the materials button, which is right next to the questions pod, you should see there that you have one handout, which is a copy of the presentation, and you can click on it to download for future use. My name is Tally Faulkner, and I'll be handling the technical support for today's webinar. If you have any issues during the webinar, you can reach out to me either in the questions pod. I'll see everything posted there in the questions pod, or you can also email me at the address listed there, which is arltap@uark.edu. The instructor for today's webinar is Stacy Williams. Dr. Williams is the director of the Center for Training Transportation Professionals and is also on the faculty of the Civil Engineering Department at the University of Arkansas. This webinar is sponsored by the Arkansas LTAP program, and Patrick Thomas with RDOT is the program manager within RDOT. Today's webinar will generate 2 hours of Rhodes Scholar credit through the Arkansas LTAP program, and you will receive a certificate which will probably be mailed to you by the end of next week. Keep in mind that you must attend the full webinar to receive a certificate. Finally, if you have a group attending with you today, please let us know who is attending with you so that we can make sure all attendees receive a certificate. To do that, please send an email with your list to arltap@uark.edu. And with that, I'll turn it over to Dr. Williams.
Good afternoon, everyone. I'm glad to see you all. It is June, it's summertime, so good time for training, I guess. I want to start off, we're going to be talking about asphalt pavement design, and I wanted to see first if I launch this poll question, just to get a feel for who all is in the audience. I want to know how many of you are pavement designers. Maybe you don't do the actual pavement design, but you do gather some of the data. You may not be involved in the design at all, or I'm not sure what that even is yet. I'll let you take just a minute and fill that in. All right, looks like most of those votes have come in. Quite a few of you, almost half of you, are actually pavement designers, so that is wonderful. We have 35% that don't actually design the pavements but do help gather the data, and then we do have a few that aren't involved in it so much, but it's a good thing to know when you're part of a public agency, local agency, that type of thing. It's good information to have. I'm going to end that poll, get you back to the presentation. So we will be talking about asphalt pavement design. There are different types of pavement design. Most of the roadways for local agencies, at least in the central part of the U.S. where we are here in Arkansas, are using asphalt pavement. So that's what we're going to be focusing on today. And when we think about that, really what we're trying to do is provide a quality pavement to handle the traveling public, provide that transportation way so that folks can move from point A to point B in a safe and smooth manner. So when we start thinking about how to put that pavement together, how to make it perform well, we've got to come up with the right materials that are going to help us get the best product possible. And then how do we combine those materials? How do we put that mix design together? So what types of aggregates, what type of binders, and then the thickness, the subgrade, and the traffic. These are all parts of what we're going to be talking about today, really that thickness design. So not what materials am I putting together, but after I get that part figured out, how much thickness do I need? The thicker the pavement, the more structure you're going to have. So we're looking at that in the context of how much support we get from the subgrade and how much traffic we expect is going to go onto the top of that pavement. And then, of course, weather plays a big factor, what part of the country you're in, what type of climate, extreme weather events, and then construction. Because construction always kind of gives us one little wild card extra at the end of the process. Now, pavement design has been something that we've done for years and years. The biggest major kind of founding study that was done was the Asho road test back in the 1960s, and that was up in Illinois. That was kind of the original study, and then things developed over time. And then 1993 was the AASHTO pavement design procedure that most local agencies, I would say, use up until more recent times. So in the 80s and 90s, we were kind of getting to a point of we can do something better, but everything we did was based on what happened in that test track in Ottawa, Illinois. They built different types of sections. They put lots of traffic on it. They loaded those trucks and drove them round and round to simulate the effects of traffic to figure out how can we do a better job of designing it. But all of that was an empirical set of relationships to say, well, we did this with this situation. Here's what happened. So we know what the mechanics are for that particular set of circumstances. But if we change those circumstances, how will that be different? How would it be different if we go to, say, Florida, and we did the same thing? Would we get the same answers? And I would say, no, you're not going to get exactly the same answers, because the materials that we use, the subgrade that we build on, those are going to be different based on what native resources we have available in different areas. So a lot of what's happening is we have this 1993 pavement design method, and that was kind of, I would say, probably the largest effort that was really kind of a nationwide, everybody's on the same page with it, but we still knew that we could do better. And so in the late 90s, a lot of movement happened trying to look at something that was more fundamental, not what depends on where you are in the country and what kind of materials are being used or what type of subgrade you have, but what is that actual characteristic, that really foundational product of what makes a difference? What can we measure that is really going to predict a more accurate outcome? And so that was the Mechanistic Empirical Pavement Design Guide, or the MEPDG. And that's really, I mean, it's a great method. It has evolved. It's still evolving, I think. So it's something that is much more complicated, though. So when we start looking at how do we implement this, we're still, it's not totally, fundamental. We're still basing some of the decisions. There are different levels of design within that MEPDG, but we have to still kind of gauge how things will work for my local area. It is also a very complicated computer program. It takes a bit of time to run all these models through the system and come out with an answer. Lots of data that has to go into creating or generating that design. So if you don't have that data, it's very hard to get a good answer. So all of the things that you need to go into the program to give you the good output, we may not have. So what do? We guess something that's close, or we come up with something that's similar, or we look at a different agency that maybe has done this that has some similar results, or we default to our state agency and what do you typically use. But the goal originally was to not do that. It's to do all of the testing and collect all of the data to really pin this down to something that's more of an exact science. But since that does not make sense overall, especially for some of the more rural local agencies, or maybe agencies that don't have a large engineering staff to do this kind of thing, that makes it really hard. So we can't transform that down to the local level all the time. So maybe we need to take a step back and go back to the 1993 guide. That's actually what I'm going to be talking about today. And how can we use that in the local context? So if you are a larger agency and you have access to this computer program, the MEPDG, wonderful. Absolutely take advantage of that. If you have access to all that data, fantastic. If you don't, we're going to look at some ways that we can make some assumptions and maybe go back to something that's a little bit more tangible for the agencies that aren't able to take advantage of that newer idea. So first of all, let's kind of back up and talk about what is pavement design in general. Well, we know that we have traffic that's going to be on top of the road. We have subgrade material that's going to be native to the area. and we need to figure out how much support that is going to give our roadway. And so we're sandwiching that roadway between those two forces to figure out how thick that pavement needs to be to withstand those forces. So looking at it from the actual roadway perspective, we've got traffic on top, subgrade support on bottom, and we're trying to figure out how thick to make that layer. So let's think about what we can control. Can we control the subgrade support that we have available? Well, if you live in one area, you have one soil type, and you may go half a mile down the road and have a completely different soil type. In some places, you may have a very consistent type of soil and things kind of stay the same, but you really don't have control over that. You can do some things to enhance it. You can change the top layer, but when you're talking about that really down deep soil structure, you have what was native to the area. So you don't really have control over that. Traffic, we don't have a lot of control over. Traffic seems to always get worse in most cases. So we know that it will probably increase. We can control some things about the traffic, but overall, we don't really have total control over that. The only thing we can really control is what we do with that layer that is sandwiched in between. Now, before we get any further, the three most important rules of pavement design are drainage, drainage, and drainage. Anything that we do in trying to build a pavement is going to be at the mercy of how well we can keep water away from that material, away from the pavement layers, away from the subgrade, and all that. So drainage is number one. We have to address that first, or we're not going to be able to get too much further with any of this. We can design all day long, but pavements and moisture, water, ice, snow, all of that, anything that's saturating the ground, that's going to be the enemy to the pavement. We're going to have increased deterioration. So we don't want that. Here's a great example of some of the types of distresses and deteriorations that you see when water is a problem. So let's look at the structure. The pavement structure is generally going to be a series of layers, and those layers will start at the surface. That's what we see. We think that's the roadway. But underneath that, we may have multiple layers of other things that are helping to give some support. The surface is that top, and then underneath we'll have a base. We might have an intermediate layer. We might have several intermediate layers. We might also have a layer between the base and the subgrade. We'd call that a subbase. So any number of layers, but at a minimum, you're typically going to see at least a surface, a base, and that's placed on top of subgrade. So the integrity of each one of those layers is important. And thinking about that drainage and the water that's going to be a problem, anytime I've got some type of deterioration at the surface, that creates an avenue for water to get into the pavement structure. So a little crack at the top, not that big of a deal. Some water gets in there, no problem, right? But then the cracks get worse, and usually they actually start from the bottom of the layer and come up. But in any case, they're getting connected through the entire layer and maybe into the next layer. So we have moisture that's infiltrating the base, and then as that progresses, that moisture continues to infiltrate into the subgrade, and a wet subgrade is usually a soft subgrade, and if it's soft, it's not giving us the same amount of support that we'd sort of hope to depend on when we design the pavement. So keeping the water out is number one goal. Now, when we have water that gets into the pavement, it's going to create some softness underneath again, from the subgrade. Also, the base can do that. So we have those openings, those avenues for water to come through. But if water can go down into the pavement structure and soften the subgrade, then asphalt is a flexible pavement. So over time, with those traffic loadings, it's going to kind of bend back and forth. And that repeated bending leads to more fatigue cracking, more avenues for water to get in. But it also means that the pavement sections above it are moving. When they move, they can actually suck some of that subgrade material back up through the cracks, and that's pumping. It's going to pull subgrade soil up into the surface, and it can also leave some of that debris, grit, not really gravel size, but some of the sand and the silt can get up into those openings where the cracks are. And then during different seasons, the summer, the pavement's going to kind of swell and those cracks will tend to close. And if you've got debris stuck in those openings, it's going to push against it, and then you create more fracture, more breakage at the edges. You have rutting, you have pumping, all kinds of bad things happen. So we can tell immediately that we definitely don't want to have any of the drainage issues. Now, this is an example of pumping and what you might see. So part of this is figuring out what types of distresses are common in your area. What do you normally see? But this is a great example of how we had some original cracking, and then the cracks that were longitudinal, that were transverse, they ended up being interconnected. And then once you have little sections that break apart, they're not really attached to the rest of the pavement. So that's fatigue cracking. Multiple directions of cracking, interconnected cracks, and that separates portions of that pavement. Now it's just like loose puzzle pieces that happen to fit together, but as soon as you have a lot of water that pumps up through the bottom, it's going to push those loose. And when you have traffic that goes across, a semi is rolling over that and it's saturated, that water is getting pushed around in those open spaces, and it'll pop some of those sections out, and now you've got a pothole. So anyway, lots of things we could talk about there, but our focus today is going to be on the pavement design part. So let's get back to that. Now, part of how we're going to handle the water is by designing ditches. The traditional, typical type of segment, cross-section of a pavement is that we have the traveled way in the middle. We have a crown section, which means the center point of the roadway, usually the center line, will correspond with the highest point in the roadway. And then we'll have a little bit of a slope out to the outer edges of the traveled way. That's going to help shed water. And then the shoulders will have a little bit more slope to move water some more. And then we go down into the ditch. We have the foreslope and then the back slope of those ditches. And the ditches are designed to carry water. Really, in all honesty, we don't want them to have to carry a lot of water, but it's better for them, the water, to be in the ditch than it is to be in the pavement surface area itself. So to get water out of ditches, one of our options is to provide some wing ditches or some turnouts where periodically we're getting rid of the water that's in those ditches. And this is going to depend on the topography, what type of slopes you have, soil type, all of that. But again, our goal is doing anything we can to get the water away from the roadway itself. Ditch shape can make a big difference. A lot of times to form a ditch, especially along a county road, a lot of times you'll see where it appears, and what they've actually done is taken a grater and they twist the blade and tilt it out to the edge, and they just run that blade along the edge. And the edge of the blade is a 90-degree angle, but it's tilted enough that we have this nice little triangle shape. And at the bottom of that ditch is very, very concentrated flow. So it's going down to that point of the triangle. So if you add more water, the elevation of the water, the height of that water, is going to go up very quickly. A better shape would be a flat bottom ditch, more of a parabolic or a curved shape, where you can disperse that flow a little bit more. So spread the water out and not have it really concentrated in that one point. And that will help the integrity of the ditches. But I'm just going to go back up here. We look at this typical cross section, and what do we design? A nice sharp little point. That's just what we do. And we don't think about it a whole lot because that's the typical cross section, but I feel like we should make an effort to quit making those nice straight little lines and put a curve out there in the ditch, because it will spread the water, which takes away some of its energy and helps prevent some deterioration and erosion in the ditches, also helping maintain integrity of the pavement section itself. Curb and gutter is used a lot, particularly in cities, residential areas, commercial areas, and that's just another way to get the water away from the pavement. So we need to make sure that all of our slopes and our design is done right to move the water away from the pavement structure and move it on somewhere else. And so back to this picture that I showed you earlier, I'm going to give you a second to type some things in the questions pod. what drainage problems do you see here? What do you think caused the problem? Anything in the picture that really jumps out as, well, no wonder that happened? Okay, we got a couple of things coming in. Any other ideas? Okay, well, what we see in the picture is that we have a lot of fatigue cracking. So there's already some damage. All of those cracks are avenues for water to soak down beneath the asphalt layer into the base and the subgrade. And so once that has happened, we've got a softened subgrade. Traffic loadings are going to press down and move the elevation of the pavement down, in addition to all the breaking and the potholes and that type of thing. You see all that asphalt, all those chunks, the rocks, they're all pushed over to the side. That's filling in the space around the gutter. But that low spot, water always finds the lowest point. So water runs downhill, and it's going to find that lowest point and it's going to sit there. So anytime we create a low spot or have pavement deterioration that generates a low spot, that's going to be a problem area in the long run. So our pavement structure is going to have to be even stronger to try to withstand that. Now in this particular spot, what you can see is we have curb on either side of the road, and the curb and gutter is there, but the drop inlet is way far away from this. You don't see any drop inlets in this. But the other piece that really stands out to me is that on both sides of the road, the slopes are where the road is really the lowest point around. Both side slopes, that grassy area, those both go uphill. So all of the rainfall that falls in this general area is flowing toward the roadway. And that's principle number one that we don't want to have. You don't want the water running to the roadway. You want it going somewhere else. So we're depending on this roadway essentially to be a drainage channel to catch all of that water. And even though we have curb and gutter, theoretically, it's going to run down over to the edge, move to a drop inlet, and be gone. But that's not actually happening because we're asking it to do too much. So, yeah, that's probably about all to say on that. I do see one other comment that came in about frozen water makes cracks. That's absolutely correct. Anytime you have a saturated pavement section, water freezes and expands. When it expands, it puts a lot of pressure inside that pavement and causes it to crack. So in addition to all the other reasons that we might have a cracking pavement, freezing water is going to make that 10 times worse. So all good comments. All right, now let's talk about the subgrade. This is the bottom layer, the foundation, the supporting structure. And really, pavement design is all about layer thickness, stiffness. The thickness is what we're trying to figure out, but that thickness will be dependent on how stiff the layer is. So you see the tire here, and there's a 1-point source. That's where the load is concentrated on that pavement layer. But that yellowish green triangle shows how that stress kind of fans out underneath. As you look downward through the pavement structure, the stiffer the layer, the more that stress will fan out. So if we can spread out that triangle and make it spread out over a larger distance, then the same load that's on top of the pavement is actually being supported by a greater area of the subgrade. So one point in the subgrade doesn't have to hold as much of that load. So the more stiffness we have in the layers, the more we're spreading out that triangle. So that's kind of our overall goal. The other thing with stiffness is a measurement. It's a term that we use called subgrade resilient modulus. I like to think of this as kind of how Play-Doh operates. Resilient modulus is kind of a fancy scientific sounding word, but it refers to the stiffness of whatever that material is. In this case, we're talking about subgrade. Now, the subgrade is kind of pliable, and it's going to change depending on moisture content. And so you think about how Play-Doh works. Think about wet soils, kind of like a handful of mud, but at the right moisture content, it could also act like Play-Doh, but it's got a little bit of a rebounding effect. So if you squeeze Play-Doh and you shape it, you mold it, it's pretty elastic, but you can definitely change the shape. But the speed of whatever is pressing on that material has a big impact on how it will respond. So if you were to take a handful of Play-Doh and you punch it with your other hand really quick, it will deform the Play-Doh some, but it's going to also resist that punch. On the other hand, if you just take your thumb or a finger and you very slowly press into the Play-Doh, you can poke way down in there. You can poke a hole all the way through it. And that's because of the time and that resistance that's there. So think of our pavement layers as kind of having that same reaction, a very quick moving load, like a Mack truck on the interstate. We're not going to see some of the same distresses on the interstate that we see, say, in a small city street at a stoplight, where a very heavy load sits there and it's going to be a very slow processing load. It can do a lot more damage. So you see some of that shoving, a lot of the bumpiness, maybe the washboarding, and that's because of the different time that it has to apply the load and how that material responds. So we can see that in asphalt layers, we can see it somewhat in base layers, we see it definitely in subgrade layers and how it responds as a part of that whole pavement unit. Now, subgrade numbers, the resilient modulus numbers, that is really a description of how much it recovers after the load is applied. It's going to depend on moisture, depends on confining pressure. If I can hold all of that really still, let's say you put Play-Doh in a box and it couldn't move very much on most of the sides, it's going to tend to hold its shape because it has that confining pressure on the sides. And then deviator stress, how much load is placed on it, and then how does that change throughout the year? That kind of goes back to some of the moisture conditions, but also freezing and thawing, different behaviors. Now, to really run a resilient modulus test, it's a little bit complicated, but we would like to know what are those numbers. This is one of the key inputs that we're going to use in pavement design. So we need to know what are some normal sounding numbers. And a lot of local agencies don't have big testing labs and things that they can fall back on to run a lot of these tests. So we need to know kind of what categories sound like normal numbers. A lot of your gravels would be somewhere in the range of 10 to 12,000 psi. Sands would be 7,500 to 10,000. And I'm putting these numbers up here, but different parts of the country are definitely going to have different ranges. Don't take this as gospel. This is just kind of a typical generic what to expect kind of number. And then we get down in our silts, 4,000 or so. Clays are going to be the softest, so they have the lowest resilient modulus numbers, maybe 2,000 to 5,000. And of course, some of them are better than others and may have lower numbers. In design, we need to adjust for that seasonal variation and moisture conditions, temperatures, what kind of cohesion we have with that specific type of silt or clay or whatever material it is and what granular size is. But typical numbers in Arkansas for just the regular in-place soils are going to be somewhere in the range of 2,500 to 5,000 psi. All right, so more commonly we talk about things like the California bearing ratio, CBR. That's a number that describes soil strength. There are also things called R value, and R value is just another characteristic. A lot of DOTs use this type of test, also referring to the strength of the soil. So the CBR test is easier to run than an actual resilient modulus type testing. So there is a very generic relationship that if you take the CBR number and multiply it by 1,500, that gives you sort of an idea of what the resilient modulus might be. That is not a magical relationship. It's really not that accurate, but it at least gives you some ideas. I wouldn't base a major design on this by any means, but something to get us mentally in the right context of what the numbers mean. And then for R value, we've also made efforts to get some type of relationship. If we measure the R value, how can we convert that to resilient modulus? we're not truly measuring the exact same thing. So again, not a perfect relationship, but that is 555 times that R value and then add 1,000, and that will get you somewhere in the neighborhood of a reasonable resilient modulus. So keep in mind, these are, kind of published rules of thumb, but not super, super accurate. So be careful when you're using them because they are rough estimates. Now, most soils are going to have a CBR value somewhere between 2 and 5 would be typical. The gravelly type soils are going to be a little bit stronger, so those will be the ones with the higher numbers. But when we have a soil that's not that strong, we can do some things to increase it. So we could mechanically stabilize, and we're going to do this pretty much all the time. If we're building a road, we want to compact that subgrade soil, and usually specs are going to tell us to do something like compact the top foot of material to a minimum of 95% of that maximum dry density, which is like a standard Proctor value, the maximum density that you get from that soil density relationship. That will happen at some optimum moisture content. But that action of creating that additional compaction, we're mechanically stabilizing, we're trying to do something to that subgrade to take it from its natural condition and make it a little bit stronger. So we pack it nice and tight so it's really solid, gives us some additional stiffness to work with when we go to put the base and surface layers on top. We can also do some things chemically that will help stabilize a soil. Some really poor soils might need lime. So lime stabilization on a clay type material is a very common thing you might see. You can also use fly ash or cement. Even asphalt emulsions sometimes are used to help stabilize a subgrade soil. And then once you've done that, you might see your resilient modulus values bump up a little bit and be in the range of 2,500 to 7,500. So we're not getting huge gains overall, but definitely helping create not only something that is a little bit more stable, but also something that is more consistent. So we want to have a consistent density across the entire area that we're going to place that pavement. Moisture has a big impact on how well these soils will behave, and different soil types will handle that moisture differently. Silts and sands don't tend to hold moisture in the same way that clays do. Clays actually have a chemically bound layer of moisture around them, so it holds onto that moisture a lot, and it also attracts more moisture. So I'm sure you're familiar with clay soils that when they get wet, they kind of swell, and then when they dry out, they shrink back down. So we have a lot of volume change. That's not optimal for being the support structure for a pavement. But whatever the soil type is, we're also going to figure out what is the moisture content that gives me the best compaction properties. So if we say we have a handful of soil, it's very dry, very powdery, and I try to squeeze that. Think of our squeezing being the same thing as compacting it in the field. If I don't have any moisture, it doesn't really hold together. There's no cohesion. It just sort of moves around, but it's not super tight. I'm not really able to squeeze that. So if we look at those individual little particles, when it's too dry, you're going to see those like in the little diagram to the left. It's got random arrangements of particles. They don't get really tightened up together because there's nothing to help them work their way into a tighter fitting matrix. On the other hand, if we put way too much water in that, what will end up happening is that all of those particles kind of get that extra layer of moisture around them. And if we compact it a lot, we squeeze real hard, they have enough workability because they're wet, they'll slide around and kind of get into layers. And those layers aren't locked together. We need a little bit of a structural matrix to help all those particles grip together so that they'll stay in place over time. If it's too wet, sometimes we run the risk of kind of a delamination type of failure, but those layers really aren't tied together from the top to the bottom. Another problem that can happen with too much moisture is that it will compact pretty easily. If you have a wet clay type of material, when you push on it, it goes down. So we do that, and we don't really have the density that we think we have, because once that water evaporates, those particles aren't really all that close together now. So we didn't get the density that we thought maybe we were getting. But somewhere in the middle of that is the Goldilocks position. That is just right. So just enough moisture that helps add some cohesion, helps things shift around, create enough workability to move those particles in closer proximity, but keep that random arrangement where the particles lock together like a skeleton. We get much better density. We get much more stability out of that material. So that is the just right part. So during construction, we are compacting, we're adding some water perhaps, maybe even some lime or cement stabilization, and we compact. We need to do some quality control, check the moisture content, check our compaction, what kind of densities are we getting. If you have a specification that dictates you need 95% compaction, or you need whatever that percent may be, then we're measuring to make sure that we're achieving that. But also visually, you would want to do proof rolling, because when we do some quality control testing, we're picking a random spot and we test that spot, but we want all of it to be just right. We can't possibly test all of it, but proof rolling is a good way to get a little bit more coverage and at least get an eyeball on it to see how does that soil behave under a very heavy load. So essentially for proof rolling, you're going to take your heaviest vehicle that you can find on that job site and drive it over that compacted soil. If it holds up, it looks solid under that load, then you're probably okay. But sometimes you'll see a little bit of a wave out in front of that front tire. It's like a little ripple that's being pushed forward. That's usually a sign that you do not have adequate density. And you might see some random soft spots, and those are things that need to be repaired right then, because they will show up later on as a place that cracks, maybe a base failure, a pothole, something like that. And this is when you can get to it to fix it. So this really is the time that you need to have an eagle eye on all of this area. Make sure you don't have those soft spots, because if you find it 2 years from now, after it's covered up with pavement, now there's a pothole, you're having to dig through the pavement, cut out the base, cut down into the subgrade. And right here, we have easy access to it to do what needs to be done right there on the front end. So, all right, at this point, I think we've got time for a few questions.
Okay, great. We have had a few questions come through. And again, if you guys do have questions that pop up either now or as we continue through the presentation, feel free to get those posted in the questions pod. The first question I have sent a little earlier: is pavement structure the same in freeways and city streets?
Yes and no. The basic idea of that structure and how it works is the same, but for freeways, you may have a pavement structure that's 2.5 feet thick. So you might have a whole lot of base, you might have multiple layers of asphalt, you may have some relief layers in between. There's all kind of different scenarios you might see. City streets are usually not as thick because they have less traffic loading. Now I say that there are cities obviously like Houston, Dallas, LA, all of that, and they have lots of traffic. But the more you separate traffic into multiple streets, city streets don't have the traffic volumes typically that an interstate is going to have. An interstate has a large concentrated, it's an arterial. That's where lots of cars are going. They're passing lots of vehicles through that one little space. So the structure has to be a lot more for an interstate than it would for a city street. So you might have 2.5 feet of structure total on an interstate, where you might have 10 to 12 inches on a city street. So same concept, but no, usually very different on total thickness.
Okay, and the other one I have, would it help to fog seal periodically?
Yes, fog sealing is a good treatment. Actually, we do have another webinar coming up next week that will talk about some surface treatments for how to mitigate premature failures and things. Fog sealing is like a very thin, very fine mist of an emulsion, so to speak. And that's going to help keep it a little more impermeable to water. So keeping water out of the pavement structure, always the goal. And Fog Seal does help to do that.
Okay, great. Well, we appreciate those questions. That is all I have for now.
All right, so we talked about what's under the pavement. Next, we'll look at what's on top. So traffic. We need to know what kind of traffic we're going to have on the pavement. And we can go out and do traffic counts and figure out what's happening now, but we're also trying to design for the future. So we really need to be able to forecast this. So we need to collect data and at least know pretty accurately what's happening now. So average daily traffic. We need traffic counts, and we also need to know the percentage of trucks. The reason for that is passenger cars and big trucks do very different things to the roadway. So if we think about the tiniest, this is the tiniest kind of passenger car I could think of as the little smart car. And we have those vehicles on the roadway. And we have these guys on the roadway, 80,000 pounds, full load, big vehicles, lots of weight. Obviously, very different loadings on the pavement. So one of our goals is to take those traffic counts and then be able to convert that into some sort of a normalized standard load. And that is called an ESAL, or an equivalent single axle load. So we're going to take that standard load and call it 18,000 pounds, and then try to figure out for the different types of vehicles, what is the load that's actually being placed? And we'll break that down by axle. So passenger cars, big trucks, and what we're going to see is that those are passenger cars, single unit trucks, and multi-unit trucks. And when I say trucks, I'm not talking about your average pickup truck, but it's the big like delivery truck type things. So looking at those vehicles, what is the weight? What is the axle configuration? And then we're going to develop a truck factor for the types, each type of vehicle. And then from that, we're going to generate how many equivalent single axle loads that vehicle is generating. So if we look at a little passenger car, maybe it's a 3,000 pound vehicle, but even just within passenger cars, we have a big range, somewhere between 3,000 and 8,000 pounds. That's going to be split up over the two axles. So obviously size, whether it's metal, fiberglass, all of that. And nowadays we need to consider, is it a gas engine? Is it hybrid? Is it an electric vehicle? Because the batteries are very heavy. So that's kind of pushing the weights of vehicles a little bit in the upward direction. I think in general, an electric vehicle weighs about 20% more than a gas equivalent vehicle. All right, so we take our two single axles for passenger cars, and then generally we'll see the same type of thing for single unit trucks, only sometimes we'll have some double axles, but we might have something like the Frito-Lay delivery truck. Chips don't weigh a whole lot, so maybe that's not that heavy. Maybe we got 12,000 pounds there. In the same category of truck, though, we might see a concrete truck. That can be 60, 65,000 pounds, quite a bit different from the potato chip truck. And then maybe we've got big dump trucks that are hauling multiple tons, 20, 25 tons of material that they can haul, plus the weight of the vehicle itself. So you can see here that we get a large range of vehicle weights. Usually these are going to end up with one single axle in front and a tandem axle in back. Sometimes the dump trucks will have triple axles. And then they're going to weigh differently, whether they're loaded or they're unloaded. Then we get to our multiple unit trucks. This is the tractor trailer type of rig. So we'll have single axle and then tandem axles, sometimes triple axles, different configurations, but this is kind of the standard. And at least in Arkansas, the weight limits they do have for particular axle configurations with an overall weight limit of 80,000 pounds. So again, we've gone a long way away from that smart car. So looking at some typical vehicle weights, cars, pickup trucks, ambulance, delivery truck, school buses, charter buses, garbage trucks, fire trucks, concrete truck, dump truck, tractor trailer. So we run the whole gamut. And a lot of times local agencies kind of feel like, well, you know, it's a neighborhood. I don't need to worry so much in this residential area about pavement structure because it's just residential. We'll just design for passenger cars. They don't do that much damage. But you do still have maybe the ambulance comes. You've got the garbage truck. You got the mail truck. You have the school bus, the fire trucks. During constructions of homes, like a new subdivision, you have all of the delivery trucks for bricks. You have concrete, all of the lumber, the roofing supplies. All of those things are much heavier loads. Maybe not all that often, but you do still have some of those. And the garbage truck is actually one of our worst offenders because they come every week. Looking at damage, how much damage does a particular type of vehicle actually do to the road? Well, we can calculate lots of stuff, but I've just put together an example here. Let's say we have 3,000 vehicles per day. 7% of that is trucks. Out of that 7%, 2% might be single unit trucks. Those are 28,000 pounds. And then multi-unit trucks at 74,000 pounds. We're going to calculate truck factors. And we're going to end up seeing that passenger cars do very, very little of the damage on our roadways. Single unit trucks do some, but those bigger semis are the ones that do most of the damage because they're the heaviest. So the green is that multiple unit, those big trucks, and then the red has a little portion, the blue tiny sliver. Blue is the passenger car. So that common misconception, those low volume roads, local agencies, city streets, county roads, they don't have a whole lot of traffic in the grand scheme of things, so I don't need to worry about a fancy design. And when we start looking at pavement design, even mixed design for asphalt, how do we put the components of aggregate and asphalt together? Some of your design standards are based on how much traffic you have, and it will be in terms of easels. And it goes from 0.3 million easels to 10 million up to 30 million and more. When you start looking at city streets, you don't have those giant numbers to think about. It's not that much. So it makes you feel like, well, we don't have to do any of that fancy stuff. We'll be okay. So I think we should be thinking about it though, because there are lots of places where new development happens. Maybe not this year, but 5 years from now, 10 years from now. New subdivisions, commercial sites, new farms. Sometimes laws change with poultry farms or logging industry, timber, all that kind of thing. And that can drastically change some of your traffic patterns that happen even in very rural settings. And that can change a whole lot of stuff that's going on. Maybe a new quarry goes in out on a county road, and that county road's been in good shape for 25 years. You've not had to do much maintenance at all. And then suddenly this new quarry comes in and those big trucks tear up the road. Drilling operations, that happened in Arkansas a number of years ago with a lot of the natural gas exploration. Some of the state highways that had been in great shape for years suddenly were falling apart, and they would resurface, and within 6 months they were falling apart again. Just because when they were designed, nobody ever anticipated that these types of traffic levels would actually impact those areas. So forecasting is important, but we obviously don't know the future. Even a new Walmart store, a Home Depot, those kind of things. When a new store comes in, traffic patterns in your town will change. And so that can have an impact. And then Google Maps. This is something that some local agencies have experienced here in Arkansas. Google Maps will tell you how to get from point A to point B, and they tell you the most efficient way. How can I get there the fastest? Or maybe you want to pick the shortest route. But whatever it is, they're trying to use that algorithm and figure out the fastest way for you to get there, because nobody wants to waste time. Sometimes that means taking a little shortcut or a detour off of the main state route. And it was one county that all the GPS things were telling these big trucks to turn off of the main highway and take this little county road, and it probably saved, I don't know, 30 seconds, but technically it was the fastest route. So all of a sudden, all of these big trucks are going through this little county road kind of back in the middle of nowhere and then coming around to hit another place to get back on that state route. Well, what happened to that county road? It was just torn to pieces. And nobody's really at fault. It wasn't on purpose, and it wasn't even that those trucks needed to be on that road. That's just one of the things that happens. So sometimes Google is our friend and sometimes it's not. So back to calculating our easels. We got to come up with those load equivalency factors, truck factors. So I think the best way to do that is to just work an example so you can see how that works. So let's say that for our situation, we had 2% single unit trucks. And those axles are one single axle, one double axle with weights of 8,000 and 20,000 pounds. So these are things that for a local agency, as much as you can get real numbers, wonderful. If not, you may have to make some assumptions or take a typical type of truck and kind of assume that that's normally what you would see. And then you can look up load equivalency factors, and these will be based on structural number and terminal serviceability, which we'll talk about a little bit later. So we will circle back. But for the single axle, the load equivalency factor is 0.041, and for the tandem axle is 0.141. Those numbers get added together because those are the two axle things that go with that singular vehicle to get an overall truck factor of 0.182. We do the same thing for our big trucks. We got 5% of those. So a single axle and two double axles. The double axles have a little bit different weights, but we get load equivalency factors for each axle, 0.213, 0.695, 0.887. And I add those three together, and that gives me a factor for the truck. Okay, so that overall factor is 1.795. And then just for grins, we'll go ahead and throw in those passenger cars. And if I take the 7% away, that was trucks, that means 93% of my traffic stream is passenger cars. The load equivalency factor, basically 0.0002 is a common number that's used. Some people prefer to not even count passenger cars because it's such a small factor. But if you really look at a passenger car, you've got two axles, and how much does it weigh? You divide that by the two axles. So sometimes you come out with a 0.004. And some people are moving to the 0004 because of electric vehicles. But overall, I think a good average is just the 0.0002. All right. Now let's calculate easels per year. So we take the average annual daily traffic, we multiply that by the percent traffic, and this is broken down by the different types of vehicles, and then we also multiply that by its truck factor. So single unit trucks, we calculated on the last slide, that truck factor of 0.182. Our traffic stream had 3,000 vehicles per day, and 2% of that traffic stream is this particular type of truck. And then this is going to end up being easels per year, but this is daily traffic, so I have to times that by 365 days in the year. So the single unit trucks will generate 3,986 easels per year. Multi-unit truck, same thing, 3,000 vehicles per day, 5% of that is truck traffic. Truck factor of 1.795, and then also multiply by the 365 days per year, and we get up close to 100,000 easels per year, 98,000 and some change. And then I went ahead and included the passenger cars, same thing, that was only 204 easels per year. So for the entire traffic stream, now I put this all together, add up all three types, and I have a total of 102,466 easels per year. And that is based on what I know right now for existing traffic conditions. All right, I've got a poll question here that I'm going to pop on there. So I'm going to launch this one. And the question is, how long do you design your pavements to last? And if you're not a designer, how long do you think they should last? All right, I'll give you a couple more seconds to fill that in. The choices are 10 years or less, 20 years, 30 years, 40 years, or more. All right, the most popular answer, about 2/3 of you put 20 years, and we had some that said 10, some that said 30, and just a few said 40 years or more. I would love it if they lasted 40 years or more. But the design period is how long do we want that pavement to last? And that doesn't mean how long will that asphalt surface last. That means how long do we want this structure to really carry us forward with. So it will include, let's say we design for 30 years. We do know that asphalt is probably not going to last 30 years, and I'll have to do some resurfacing. But what I'm trying to avoid is doing a major rehabilitation or a total reconstruction for a period of 30 years. So yes, it includes some maintenance. No, I shouldn't have to do anything major for that time frame. So the design life of the pavement is usually set by a policy for your particular agency. So a lot of folks will use 20, a lot will use 30. When I was in college and learning how to do all this stuff, I thought, wow, 30 years, that's forever. That just lasts forever. We'll never have to see this pavement get designed again. Well, now that I'm older, I realize that's not as long as I thought it was. So policy is usually something that gets set for a number of reasons, not just the pavement design part, but maybe 20 years is enough. A lot of local roads are designed with a 20-year design life. Highways typically will have more of a 30-year, but there's also a perpetual pavement concept that's gaining traction over the last decade or so, that we designed that the overall structure, we want it to last forever. So I guess if you had to put a number to it, it would be a 50 or 60-year design life, but we would love for that part to last forever. So that means building up the structure quite a bit, and then the top sections could be replenished over time and not have to do so much of going all the way back down to the subgrade to fix something. We should be able to make our fixes in those upper layers that are easier to get to, which means it's a more economical type of fix, and it's a one-time cost up front to really beef up that structure down deep. Now, part of the problem with that is it's more expensive to do that, and a lot of our local agencies are governed by elected officials, also state and national agencies. So with limited budgets, it's a hard sell to be able to say, let's design for 50 years and this will last forever. That prepares for generations to come, but it may not be that high of a priority for, say, a governor or a mayor or a county judge or whatever you have in that agency. Maybe they're going to retire in 10 years. They really want to make sure it lasts the 10 years. Maybe not quite so interested in the longevity past that point. So it kind of depends on the goals of the ones who get to make those decisions. So I think as a pavement designer, I would love for everything to go to perpetual pavements, but that's a hard sell. So I've got another poll question for you. I'm going to pop this one up. What type of population growth are you seeing in your areas? You have a lot of growth going on. We're here in Fayetteville, Arkansas, which is in the northwest corner, and it is one of the fastest growing areas in the country. So we are seeing a lot of growth, but there are some areas that aren't changing a whole lot, and even a few places in Arkansas that I would say the populations are declining. All right, so far most folks are saying they've got a little. We've got some that have said a lot. Nobody said their population is declining, but we do have a few that said there's not much change. All right, I'm going to go ahead and close that one out. Now, population growth is important because it relates to traffic growth. The more people there are, the more people going places. We have to figure out what that growth factor is, because that's going to tell us our expected increased levels of traffic. And that's going to be for the design period. So think of it like money in the bank, and you get a loan and you pay a particular percent interest for a certain time period. Those same types of calculations are going to be used for growth rates for population and for traffic. So we figure out what percent traffic increase we expect to have over that design period, and we need to total up how many total easels is that going to mean. We calculated easels just a minute ago, but that was just for this year. We want this pavement to last more than this year, so we need to know all the traffic that's coming. So now we're getting into forecasting things in the future, and we don't know where will the subdivisions be, where will the Walmart stores be, the Home Depots, where will new areas of development happen, all kinds of changes and things that can happen. So it's kind of, we need that crystal ball to do a best job of it, but we do the best we can. All right. Now, you can find this in lots of apps online for interest rate and that kind of thing, or you could look it up in a table, but those factor tables are written so that your interest rate is essentially the growth rate or the growth factor that we're going to use for traffic. So let's say that we use a 20-year design life, and let's say that we assume a growth rate of 4%. I'm going to go in the table to a period of 20 years, and I want to see what, if I have that interest rate happening for a certain population over time, I want to know what is the future value of that level. So I take the whatever my easels were, and I find this growth factor. For the 20 years, 4% interest, my growth factor is 29.7781. So I take my easels, multiply that by the growth factor. Now I'm looking at over 3 million easels. So that number jumped up really fast. But that makes sense. It should. I'm going to design this for a long time. Now, there are some other traffic factors that I need to think about. One of those is going to be how many lanes do I have? So number of lanes, if you have all 2-lane roads in your county, this probably doesn't affect you much, but you do know that if there are 2 lanes, some traffic goes one way, some traffic goes the other way. So we do have traffic split in direction, but what this is talking about is a design lane. So let's say you have a 4-lane roadway, like what's shown in the picture. You have more than 1 lane going the same direction. The thing that's important for this is that truck traffic typically stays in the right lane. Most of us would like for them to stay in the right lane. They don't always, but usually that's kind of the designated truck lane. So our heavier loads tend to be on that outside lane. And if we think that, you know, most of the damage or the loads are going to happen over there, we're going to assign a truck factor. It's typically somewhere between 0.8 and 1.0. If we really think that all of those truckloads are going to be in one lane, then that lane has to be designed for all of that truck traffic. But if it's going to be kind of split, then we can, you know, shave a little bit off of those easels. And then directional split. We do have some traffic going in each direction. If it's a 50-50 split, then we just divide it in half. But we have a lot of situations where one side is actually going to be carrying more load. For instance, if you have a quarry near a county road and all the trucks come out, they always turn right to go up to some main area to go toward town or whatever. If the loaded trucks are always in this lane, and when they come back to the quarry and they're empty to reload, they're always in that lane. Now I have a difference in those 2 directions. So if everything is 50-50, that's how we're going to treat it. But in some of those areas with logging operations, quarries, chicken houses, all that kind of stuff, or it could even be what is the garbage truck route? When are they loaded the heaviest? That could actually have some impact as they go through their routes. So think about that. And if we don't have everything even Steven, then I don't need to divide this 50-50. I need to give preference to that heavier side. And that's how I need to do the design. All right, so let's do a few examples here. I think that's the best way to work through it. Let's say that let's bump our design life up to 30 years. Let's stick with our 3,000 daily traffic. Let's say we just have 2% trucks. I think for local agencies, that may be realistic in some cases. And if 1% single unit, 1% multi-unit, and we'll go ahead and say it's 50-50 split, and our growth rate is 2%. When I run those calculations, I come out with about 500,000 easels, 0.45. So that's, in the grand scheme of pavement design, that's a very small traffic level. So not a whole lot to design for. But, yep, there's our breakdown of the proportions of the different trucks. Even at 1% of the big trucks, they're still doing most of the damage. But what if I increase growth? Maybe the school districts changed, some of the dividing lines changed, or maybe just a new subdivisions going in, you're going to see growth on one side of your town. So let's bump our growth rate from 2% up to 4%. Let's see what happens. We'll keep everything else the same. Now we've gone from 0.45 easels up to 0.63 million easels. So definitely a change. Still the larger proportion of damage done by those big trucks. All right, now let's increase truck traffic. What if a Walmart distribution center is built close by? You're going to see a definite uptick in the number of trucks. So let's go to 12% trucks. We'll say 10% multi-unit, 2% single unit, 50-50 split, 2% growth. Now we're going to jump up. That's a big difference. Okay, so over 4 million easels, again, most of that with the multi-unit trucks, that's a big change. So, and it was a big change in truck traffic. The overall traffic stream didn't change so much, but a large uptick in the percentage of trucks. In fact, that's about an 800% increase. So that's the kind of thing you would feel in the town. You would know that things are changing, but pavement design wise, do we know something like this is going to happen 20, 30 years before it happens? We don't always know. So it is hard to forecast all of those things very accurately because we don't know the future. Now, what if we increase the trucks and the growth? So keep what we had, the 12% trucks, and we bump the growth rate up to 4%. Now we're at 5.6 million easels. And that is more than an 1,100% change from where we started originally with this example. Okay, well, maybe you're looking at it thinking, you know, we don't have that much traffic. We've got a lot of really low volume roads. So let's say we have a 400 average daily traffic. So pretty low. Let's go ahead and keep our 30-year design life with 2% trucks, 1% single unit, 1% multi-unit, 50-50 split, and a 2% growth rate. That's going to come out at like 0.06 million easels. That's kind of not even on the scale of a lot of our design methods. So very, very small, but it doesn't mean that pavement design is not important. If we bump up our truck traffic, maybe we got some drilling operations going on or a new logging facility, and so we get a lot more trucks added on. Now we can jump that up to 0.75 million easels. Still not huge in the grand scheme of the world, but it is an 1,150% increase from what we had before. So that will definitely have an impact on how your pavements are going to perform and how that performance and longevity is affecting those traveled ways. All right, this feels like a good spot to stop and talk about things.
Okay, yes, we have had some questions come through. The first one regarding EV vehicles. California is proposing a new fee for EV cars. Since a typical passenger vehicle accounts for a microscopic fraction of an equivalent single axle load, even if a heavier EV doubles the value, its structural impact remains near zero compared to heavy truck traffic. From a pavement design standpoint, is there a technical justification for these fees, or are they purely intended to replace lost fuel tax revenue?
That one's a little touchy. There definitely is a difference in weight. Now, if you have a lot of trucks, then even the EVs are not. I mean, you're going to increase the damage by roughly, I would estimate, 20% of what normal passenger cars would. But also, it's those heavy trucks that are really causing a lot of what's going on. So I don't know if it's fair to really say that that's a proportional, if they're doing some kind of a fee for that type of car, is that fair to say that's where the damage is coming from? I'm not sure that that's the intent. However, they will cause more damage than the typical passenger car. So in a comparative, relative type of sense, yes, I can see the thought process. Is that where all of your damage is coming from? I don't think you're going to start seeing EVs just randomly tear up roads all of a sudden, especially if you normally have trucks. Now, if there's an area where you don't have truck traffic so much, and you start seeing an uptick in deterioration, I also wouldn't say it's all because of electric vehicles. I would say it's probably a combination of things. All that to say, yes, I think it contributes. Is it the total cost? Should they have to be the ones paying the fee for it? Probably not fair. But also, if it's something new, I can see the thought process of it being an opportunity to recover some of the cost, because pavements are so much more expensive and we really never get the budget for maintenance and things. Fuel taxes go a long way, but they don't near cover the cost of what needs to happen. So there's never enough money, and it is, I'm sure, a way to figure out where can we get a little bit more to add to the budget.
Okay, great. And kind of tying into that question, we also got a question. What if your city has an Army, Navy, or Marine base? Do you need to consider the weight of those vehicles in the design? I imagine that they have a high gross vehicle weight.
Yes, absolutely. So if you have that, a lot of those vehicles are definitely heavier than, the typical passenger car. So their Humvees are going to be a little bit heavier. Army bases typically handle their own design for pavements. I mean, they kind of do their own thing. But if there's some of that intermediate where vehicles are using your city streets or county roads or something like that, that would be something I would definitely take into account, because those will be heavier than your standard passenger cars. And they have a lot of specialized vehicles to consider. So probably more in the range of those single unit trucks.
Okay, and then one more question we've got, and I'm sure you've never been asked this one before, but is concrete paving a better choice instead of asphalt?
Well, I will preface this by saying that my background is in asphalt, so absolutely not. No, but really, there are times that asphalt is clearly the better choice, and there are times that concrete is clearly the better choice. Particularly looking at subgrade types, if you have a weak subgrade that maybe a lot of underground springs, water from subsurface sources that you really don't have any control over, that continue to make an area very soft, it's really hard to get a good asphalt pavement, get good compaction for an asphalt pavement. So that might be something to think about. In general, though, asphalt will have the lower initial cost. If you look at life cycle cost analysis, the arguments can be made both directions. Concrete tends to last longer. It costs a lot more on the front end, but it will last longer. You don't have to do as much maintenance during that 30-year design life. Asphalt, we do a 30-year design life, but we also plan to have maintenance. So to the public, after say 12, 15 years, you go out and you're putting a new, you're doing an overlay, something like that. Wow, they're already having to repair that road. Well, no, that was a planned maintenance activity to extend the life of the entire structure. To the public, it looks like that road only lasted 12, 13 years. Concrete, you don't see folks having to go out and do as much repair work just because the material is different and the repair strategies are completely different. The downside of concrete, though, is when you do have to make a significant repair, that road is shut down for a considerable amount of time. So you've got to wait for the concrete to cure. An overlay, you can get in, get out, traffic's back on. Not to say that every asphalt project goes nice and quick, but concrete projects, if you're doing a lot of work on concrete, you're going to have a lot more traffic delays. So depending on what traffic you're trying to maintain, if you have options for detour routes, a lot of the delay costs get really bottled up with concrete. So most of the roadways, like 96 point something percent of local agency roadways in Arkansas are asphalt roadways. It's a little simpler, more straightforward to do the maintenance on. So I think that's why we see that the most. There's some, political between the two camps of asphalt and concrete. I personally would say asphalt, unless you have very heavy traffic levels, if you're seeing a lot of running around intersections, and a lot of times people ask me this for parking lots. I never recommend asphalt next to a dumpster because a heavy truck is coming in and they're going to sit there and they're going to move that load around while they're dumping that dumpster box. And you always see those ruts right there. So that's a great place for a concrete pad. So I will give you the typical consultant answer. Asphalt is my favorite, but of course it depends on the situation.
Okay, great response, and appreciate those questions. That is everything I have as of this moment.
All right, very good. All right, so we've talked about subgrade, we've talked about traffic. Now we're going to start putting that together to figure out how much structure we need. And there's something called structural number. This is kind of the key concept of that 1993 AASHTO pavement design process. This is a factor that puts the pavement layer properties and thickness together, and it's going to include a whole lot of stuff. So one of those is reliability. How important is it, that this is a reliable design? We're going to have some standard deviation to think about because the materials, the processes that we're using always have variability. We're going to include our traffic loadings, which we've talked about, our soil strength, which is all the subgrade stuff we talked about, and then also a general factor of serviceability. And this deals a little bit more with how the traveling public perceives this project or this roadway. Let's look at each one of these a little bit more closely. Reliability is a number that describes the probability that the design is going to succeed for the period that I've chosen for the design life. So if it is a very high classification roadway is what I'm calling it, but what I mean is like traffic levels. And if you look at your breakdown of the streets, we're going to have local streets, collectors, and arterials. Arterials tend to carry the most traffic. They're thought of as more critical. So I want a very high reliability level for those arterial roadways where I might be apt to accept a little bit lower reliability on, a subdivision street or something like that. So those local roadways, maybe 80 or 90% collectors are the ones that get people from their houses or their businesses to those main thoroughfares. Those are the collectors. 85 to 95% is typical. So it's basically saying how much risk are you willing to accept that something could possibly go wrong. So arterial 95% means 5% chance that something is not designed quite right. And then overall standard deviation. This describes how well the data fits the design equations. And we know that those equations were developed for one location with a set of materials that may or may not match the rest of the country. So we're saying, how certain are you that all of your design inputs are correct? And that goes beyond just the traffic and that kind of thing. But for asphalt pavements, there are lots of places that things could vary. When I make the mix design, the aggregates that go into that mix have variability. The binder, the oil that we use in that mix has variability. Everything that we do with asphalt has some component of variability, and our goal is always for it to be completely consistent, but we know it's not in reality. So our standard deviation value for asphalt pavements is typically around 0.4 to 0.5, which is honestly a large number, but there are lots of places where things can vary, even when we get to the construction phase. Next is the traffic estimate. This is the one that we've talked about. We're figuring out that estimate for the design life of the pavement. How many equivalent single axle loads are we expecting to put on this pavement? So separating that out by truck, type, the axle configuration, what kind of load we expect, and then all the other factors. What's the growth factor over that design life? What's the directional distribution, lane distribution? In other words, how many 18,000-pound axle loads are expected to pass over this roadway during its design life? And then resilient modulus of the subgrade. This is that recoverable strain or the bounce back, how much it will recover every time a load goes over it, how much does it rebound? So it takes the not only that into effect, but also moisture conditions, seasonal effects, and gives us a general value that will describe how much support that subgrade is going to provide to the pavement layers. And then last is serviceability. And this is the one that's more of a public perception kind of thing. So if you took people and said, okay, drive down this roadway, and on a scale of 1 to 5, what do you think? And if they did that when a roadway was brand new, we would hope they would give it all 5s. But sometimes people are picky and they don't give it a 5, they give it a 4. You know, it's pretty good, but this spot, I felt a bump or, whatever. So if we had them rate the roadway, scale of 1 to 5, most of them would probably say somewhere between a 4 and a 5. So the initial serviceability on average usually is somewhere between a 4.2 and a 4.5. But then if we did the same thing at the end of the pavement's life and we had people drive down and say, now drive down it. What do you think? What would you score? And if you were to tie a number to the condition that folks are like, this has got to be fixed. It's bad. It's dead. It's over with. We need a new road. Somewhere between 2 and 2.5, folks will probably kind of give up on it. That's how they would score it when they think it's at a point that it needs to be fixed. So this is, public perception. There's not a whole lot of science to what actually makes that number. But by and large, these are the kind of numbers that people will give you. So when a road is used up, it would score somewhere around a 2, 2.5. Now, the number that we're actually going to use in the calculations is the change of serviceability, which is the loss that the public will typically tolerate. So if we're starting at a level of, say, 4.2 and going down to a 2.5, that's a difference of 1.7. And folks will typically tolerate anywhere from 1.7 serviceability loss down to 2.2. So we go back to our calculation, and we're going to include this delta PSI. That's our change in serviceability, and that's the serviceability index. So difference between the initial and the terminal pavement service index, or how much quality are we going to allow there to be lost? Now, once we have all those numbers figured out, we go to this cute little equation here, and it's pretty ugly. So we've got the log, W18 is our easels, S sub 0 is the standard deviation, the Z sub R, that's our reliability, structural number is Sn, and that's actually the thing that we want. So when I start looking at this equation, it looks like, well, you just plug in numbers and you get an answer, and that answer is log base 10 of our easels, but we already know easels. That's not the goal. The goal is to figure out what is my structural number. And structural number is tied up here at the beginning section of the equation, and then also at the bottom of this really messy part of the equation. So solving this for structural number is not that easy. So when they developed this equation, they came up with a nomograph, and this will help us work that problem. So out here on the left, this is, I guess, what I would call old school engineering. Nomographs are kind of cool. So we look at what our reliability value is, and that is on a scale. And then we know our standard deviation that we chose, and we can draw a line between those two things. And that straight line is going to continue across to a turning line. So I'll stop there. And then from that point, I'm going to go through this next scale, which is estimated total 18 kth equivalent single axle load applications. Those are our easels. So, and that's in millions. So we take our number of however many million easels, we put a point there, and we're able to go from this point on the turning line through the easels number across to the next turning line. Then we look ahead, and it's asking us for resilient modulus. And we're going to go from that turning line across through the resilient modulus until we hit the edge of this graph. So the big square part, we get to the border line of it. And then we're going to go straight across horizontally and hit one of these lines. There are 6 different lines that are drawn, and each one of those is related to a certain design serviceability loss, or delta PSI. So we find the line that corresponds with our delta PSI. The example that's shown here is the 2.0 line. So I go until I hit that line, and then I drop straight down, and it looks like I'm at a 5. That means that my structural number is 5. So let's do a different example. Let's do reliability of 95%. So that's going to be the yellow dot right over here on the left, 95%. And my standard deviation overall is 0.45. If I put that dot there, excuse me, come across to the turning line, go through my easels, I put the dot, and then I go to the next turning line, and then I put my resilient modulus dot, and I do realize that the dots are big so you can see them, but it also covers up a lot of the numbers. But the line then goes through that point to the edge of the graph. We have a delta PSI of 2.0, so I need to pick the line corresponding with the 2, so the yellow arrow highlights that line. I go straight across to that point and then drop down, and I'm at about a 5.9. Yep. So fun stuff. There is a better way, of course. So if you go to, there are a number of websites that have this. One of the ones I like is pavementinteractive.org. And if you go in their website to the design section and look at structural design, that will take you to a description. They have the AASHTO guidelines for both asphalt and for concrete. Of course, we're talking about asphalt today, but the asphalt is flexible, so that's the 93 AASHTO flexible pavement structural design. And then you click that link, and it takes you to another link, you click the same thing, and that goes to an input page where you can put in all of those input values that we talked about. So your total design easels, enter a number. What's your reliability level? Enter your number. Your combined standard error, standard deviation overall, enter that number. And then your initial and your terminal serviceability, it will calculate the delta PSI for you. And then you can put in, if you've got base layers or something else going on, you can put a lot of stuff in here. Then it gives you what is your design structural number. So over here under number 1 at the output, calculation parameters, you're looking for the design structural number, SN. And for the numbers that we used in that last example, we've got 5.955. So the picture version that we did came out pretty close, but I will caution you, when you look up that nomograph, that graphic is so specific, and a lot of times people will find it in a book and you want to be able to draw on it, so you make a copy. Be careful running things through the copy machine. If it gets skewed or twisted or stretched, that's going to change all of those numbers. And of course, entering it in a computer program is also a little simpler than that. But anyway, those are some ways to get to this number. And that's kind of our goal, is getting to the structural number. So that is our output. So that's one of the options. There are multiple places to get that. You can also do an Excel spreadsheet and use the solver function to make it generate that structural number for you. So what I've done next is taken a number of examples with different traffic levels, different truck percentages, different breakdowns on multi-unit, single-unit trucks, different soil resilient modulus values, and just to give you a concept of what is the structural number that you get from those combinations of factors. So starting out over here, I've got 3,000 for my traffic level, that's vehicles per day, 15% trucks, and that breakdown is 11 and 4%. Resilient modulus of the soil subgrade is 3,000. That generates a structural number of 5.68. If I were to take that resilient modulus value and say I had a better soil that was maybe 5,000 PSI, my structural number is 4.84. Okay, that's a lower structural number, and that means I need less structure for this pavement for given traffic conditions if I have better subgrade. So increasing my resilient modulus from 3,000 to 5,000 means I have to have less structure provided from the pavement, because the subgrade is going to do more of the work for me. And then if I go to a 7,000 PSI subgrade, that drops my structural number on down to 4.34. And this is all given these inputs over here on the right for the same reliability, standard deviation, and delta PSI. So now if we do the same thing, but we have a smaller percentage of trucks. So now 3,000 ADT, but only 7% is trucks, 5 and 2 for the multi and single unit. I get for the 3,000 resilient modulus, I get 5.12. For a middle type of soil, I get 4.34. And for a good soil, 3.86. So the better my subgrade soil is supporting, the less structure I have to have provided from the pavement for given traffic conditions. And then this last one, there's only 3% trucks. So overall, the numbers in this bottom section are smaller than the numbers in the top section. That's telling me that for lower amounts of traffic, my pavement has to handle less loading. So I don't have to have quite as much structure because I have less traffic loading that's going to be applied. Okay, what if I take this down to only 1,000 vehicles per day? And I still have those same combinations, 15% trucks, resilient modulus levels of kind of a low, medium, and high, 3,000, 5,000, 7,000. Then my structural numbers up here are 5.16, 4.37, at 3.90. When I drop the truck percentage, you can see that that also brings down the structural number. So I have less structure required for those conditions. And then same thing, I drop it again when I have only 3% trucks. Then I did one more set of calculations for 250 vehicles per day. So very low, but this might be an area that not much trucks, but a good percentage of them, or not much traffic, but a good percentage is trucks. And the bottom of the graph, we're down to where not much of it at all is trucks. And those numbers are ranging between 4.25 on down to 2.22. Okay, so same set of factors, but only 250 vehicles per day. So you can see what that does. So what does that mean in the context of the world? Well, how does it compare? In fact, someone asked, how does this compare to, city streets compared to interstates? Well, a city street, if you only have 200 and something vehicles per day, you can see that structural number would be pretty low, like down in the 2s, low 3s, something like that. I have an example here. Interstate 40 through Central Arkansas between Memphis and Little Rock has, I believe it's at least one of the highest truck percentage routes. So tons of truck traffic. In fact, when we report the numbers, it's about 60% trucks. That is just unheard of. And people always think that's a typo. It is not. We really have that many trucks. When you look at, say, a 55,000 daily traffic count and 60% trucks, that comes out to be a structural number of somewhere around 10. So that is absolutely huge. So that is an extreme case, of course, but just to put that in context, a structural number of 10 is very different from a structural number of 3. Even though our concepts of how we're doing it is all the same. All right, any questions up to this point?
Yep, we've had one question come through. Can you explain standard deviation again and what happens to your design if you choose a lower or higher standard deviation?
Okay, good question. I kind of think of it as a little bit of a fluff factor, but it is really just kind of a factor to consider the variation that you experience with asphalt pavements and how we design the mix, how we place it, how we compact it, the whole construction aspect, and what all is going to end up, all the variability that we will see. 0.45 is a good typical number for asphalt pavements. Concrete is actually a little bit more consistent, a little bit easier to make it consistent. So you'll typically see standard deviation numbers down around the 0.35 for concrete. So a little bit of difference there. But what's going to happen in your design if you take, let's say that you chose 0.4 and you thought, well, I think a typical number is 0.45. So if you calculated whatever structural number using a 0.4, when you increase the variability, you're going to have to account for that in your structure, which means you're going to need a little bit more structure if you have more variability, because there's kind of more chance that something goes wrong, if you want to think of it that way. So the higher the structural, or higher the standard deviation, the higher the structural number is going to end up being.
Okay, great. Well, I believe that is everything for now.
All right, very good. Well, in our next session, we're kind of getting to the end of the process, but it's what do we do with that structural number? So now that we have the magic number, how does that translate to actual pavement thickness? So we're going to combine the layer properties and the thickness and figure out something for each layer of our pavement. So we're going to have a surface. We know we have a subgrade, and we need something in between it. That's going to be our base layer. And sometimes we have a sub-base layer. So for everything above the subgrade, I need to look at the depth of that layer. I'm going to have a layer coefficient, and I'm going to have a drainage coefficient. So let's dive into those. Now, layer coefficient is kind of a number that describes the stiffness. And stiffness really is the key to how well it's going to perform. The stiffer the layer, the more structure we're getting from that layer. Now, an asphalt mixture in general is going to give us a 0.44 layer coefficient. And that, is it the right number? I don't know, but it is the number that's been used for, I mean, it's kind of the standard number that's been used forever. So the assumption is that for a standard asphalt mixture, we're getting a layer coefficient of 0.44. Now, if it's a recycled material or a base course or some different types of asphalt, that will drop a little bit. But the highest number you're usually going to see is a 0.44. Base course down around a 0.36. A surface treatment is a little bit lower than that, down around a 0.25. And then when we start getting into base courses and soil cement, those types of things, we're lowering that even more. A lime-treated subgrade can be treated as one of our pavement layers because we've done something to mechanically change that layer. That's going to be a 0.07. And then your standard class 7 base course is usually treated as a 0.14. So those are some of the typical numbers that are inputted. So remember that we have a load on top, and we're trying to spread out that load as much as possible. So the higher the layer thickness is, or the more structure we get from those layers, the more we're going to be able to spread out that load and reduce its impact on the subgrade, which is really the ultimate piece of the foundation. Now, drainage coefficients, they don't apply to the surface layer, only the base and the subbase, but that's whatever's underneath there. Like how much does it stay, how long does it stay wet? How long does it stay saturated? Values are typically going to range from 0.4 to 1.4, and if it's very average behavior, we're going to stay at a 1.1, which essentially is a factor that doesn't do anything to that number. Poor drainage will be something less than 1, and excellent drainage will be something greater than 1. So 1 is kind of our baseline average, and then we can reduce or increase that as needed. In general, excellent drainage would be that we can get from fully saturated down to 50% saturation in about 2 hours. Good drainage would be to get to 50% saturation in about a day. Fair drainage is in 7 days. Poor drainage, it would take a month. And very poor, it just really does not drain. So remember, we're talking about what's down underneath. After everything's been saturated, how quickly does that get removed? And there are some places where it really does not ever get removed. So the other question is, how often does your subgrade get saturated? The more often that happens, the more damage you're going to see. So we have the subgrade to consider. We also have the crushed stone base, and the base is probably not going to stay saturated as often as the subgrade would, but depending on your circumstances, that may not be true. And that's largely a function of where the roadway is, its proximity to drainage areas. Is it downhill from a large, watershed, that kind of thing. We can also design with full depth asphalt, and that would mean that we have different layers. So maybe instead of a crushed stone base, we have an asphalt base. In Arkansas, we use 1.5 inches or 37.5 millimeter asphalt mix. A lot of states will use a 25 for their base. Arkansas uses an intermediate course that's a 1 inch top size aggregate or 25 millimeter design. A lot of states will use a 19 millimeter. And then our surfaces are either 1/2 inch or 3/8 inch. So the closer you get to the surface, the smaller the aggregate particles are. It's a smoother surface for that traveled way. Now, in terms of constructability, before we get into a lot of the design and how to pick out that thickness, we need to think about what's reasonable and what makes sense. The worst thing you can do as a designer is design something that's really perfect on paper, but it can't be built. So that doesn't do anybody any good. So from a construction aspect, what we know is that asphalt compacts best when we are compacting a lift that's about 3 to 5 times its nominal maximum aggregate size. So nominal max aggregate size is basically that pretty much the largest aggregate particle that you see in the mix. So that, let me go back one slide. Right here, the surface, a 1/2 inch or 3/8 inch, that is the nominal maximum aggregate size. That's kind of the name of that type of mix. And the deeper in the structure you go, the larger those particles are. So I can compact a base layer that's quite a bit thicker than I would compact at once when it's a surface mix. So for surface, if it's a 1/2 inch top size, 3 times that is 1.5 inch, 5 times that is 2.5. So somewhere in that range is going to give me the optimum compactive qualities. And one of the key factors in being able to produce a good asphalt pavement is to be able to get density. So I've got to compact it well. So I'm looking for a surface somewhere between 1.5 and 2.5 inches thick. That's why most of our overlays tend to run around 2 inches. A binder or intermediate course might be 3 to 5 inches. A base course will be something thicker, usually 4.5 to 6, maybe 7 inches at a time that we can compact. Okay, so keep that in mind as we start looking at these thicknesses. So our structural number, if we go back to the equation that I showed a few slides back, structural number is equal to the depth of layer 1 times its layer coefficient times the depth of layer 2 times its coefficient times that drainage coefficient. And then same thing, if I have a third layer, then I would keep including sections of that. So what's happened here is I calculated, this was, I believe, that very first example we did. 3,082, 15% trucks, 3,000 PSI resilient modulus of soil. That gave us a required structural number of 5.68. So I want to add all this stuff up and get something that's at least 5.68. So let's say my first attempt is that surface layer is going to be asphalt. And let's say I put 4 inches of asphalt, that would be 2 surface lifts, times the layer coefficient for asphalt is 0.44. And then my second layer, let's say we'll try 14 inches of crushed stone base, which has a layer coefficient of 0.14. And I guess it's going to drain pretty average, so a factor of 1.0. So I take those two segments, multiply the factors, and then add those layers together, and I get a structural number that those layers would generate of 3.72. Well, that's not enough because I needed 5.68. So looking at this scenario, that's not going to be good enough. The other thing is I don't really have that third layer, so just keep in mind I did not include that portion. But this 3.72 is not enough, so I need to go back to the drawing board. So let's try this again. What if I do 2 inches of surface and I put more asphalt? So let's do an intermediate binder type course of 4 inches and increase my class 7 crushed stone base to 22 inches. Then what do I have? Okay. Well, 2 inches, 0.44, another 4 inches, 0.44. This layer will have a drainage coefficient. I gave it a 1.0. Same thing with the class 7, but I made 22 inches of that with a layer coefficient of 0.14, and that gave me 5.72, and that is enough because I was required to get something at or above 5.68. So this pavement structure, 2 inches of surface, 4 inches of intermediate, 22 inches of crushed stone base on top of this given subgrade, does give me enough structure. So that's an option. All right, a couple of other options. What if I look at different combinations of layer thicknesses and layer types? The middle one that I've shown here is a 4-inch surface, so that will be placed in 2 lifts. 4 inches of an intermediate binder course, And then 15.5 inches of class 7 gave me a 5.69. That just makes what I need. Or I could look at full depth asphalt and do 4 inches of surface, 4 inches of intermediate, 6 inches of base. And that ended up giving me a 5.68, which is also just enough. So you can see there are infinite combinations of things you can do and continue to calculate, what if I try this? What if I try that? And so that is the design process, is going through that over and over. As a rule of thumb, for good to average drainage, it takes a little over 3 inches of aggregate base, the crushed stone base, to replace 1 inch of asphalt surface or binder intermediate mix. So that's kind of a rule of thumb when you're trying to think through some options. It's a very general rule of thumb, but typically it'll work out about like that. All right, looking at some design alternatives for a different situation. 1,000 vehicles per day in traffic, 7% trucks, medium subgrade, 5,000 PSI, and the structural number required was 3.9. So if I do 2 inches of surface, 4 inches of an intermediate course, 9 inches of crushed stone base, that gives me a 3.90. Or I could do more of the class 7 base, less of the asphalt. That would give me a 3.93. That also works. Or I could go full depth asphalt and have base, binder, and surface mixes of asphalt and get 4.0. All of those would work. Now keep in mind, all of these have different thicknesses. So think about what happens if you are paving under an overpass or you have some type of a vertical clearance limit. Sometimes that will dictate how thick your pavement section can be. And then the final alternative with that really low traffic level, 3% trucks, good subgrade, our structural number there was only 2.22. So what kind of pavement layers will work for that? If I try 2 inches of surface over 10 inches of class 7 base, I get a structural number of 2.28, which is enough. I could also do 6 inches of class 7 with 4 inches of surface. So 2 lifts of a surface mix on top of that. That will also give me enough structure. Or I could place a base mix right on the subgrade and then add an 1.5 inch surface mix, and that will give me a 2.28. One final option would be 3.5 inches of surface. You could do that in 2 lifts, where the first lift was 2 inches, the second lift was 1.5 inches, and then put that over 6 inches of class 7. That's an option. So as you can see, there are lots of ways to get to a reasonable answer, and lots of ways that you can use your pricing of the different materials to see what's best in your current situation. Class 7 base in Arkansas anyway right now is running somewhere around $40, $50 a ton. So if you do 1 lane mile at 8 inches of depth, that's about $145,000 or $18,000 per mile per inch of base. Asphalt surface, and these are ballpark numbers for given situations. Obviously, there's a wide range of numbers we could throw in here, but about $180,000 per lane mile for asphalt surface that's 2 inches thick. So you could say $90,000 per mile per inch, or lane mile per inch. Okay, now the other question that comes up is, what about the existing pavement layers? What if you already have some layers and you're looking at trying to beef that up, but using the structure that you have? You're not really starting from subgrade up. Well, you can get some structural benefit from those layers that are already there. So if you have an asphalt surface in fair condition, you're not going to get the full 0.44 layer coefficient, but you might get 0.35 or so per inch. If your asphalt surface is in critical condition, maybe bump that down to a 0.2 to a 0.35, depending on how deteriorated it is. And then you can see as you go down in condition, you're getting less and less existing structure to add to your total overall structural number for that design section. If you're down aggregate base that's in bad condition, you're really not getting anything at all out of that. So, not too long ago, I was in Indianapolis and went to the Motor Speedway, did the whole tour, and it was all about cars and racing and things. But the cool thing was they did have a little display with all of the different pavement layers at the Brickyard. And that red layer, it's actually, if you can see my cursor, it's right here in the middle at number 8. That is the original layer and how it got its name, the Brickyard. But you can see all of these different layers and different surface treatments, different layers of asphalt as they've repaved it over the years. That is a significant pavement structure. So pretty cool. Just kind of a little extra for you. So are there any questions?
We have had a couple come through. I know we're getting really short on time. One question pertaining to the calculations. Why is the subgrade not considered in the SN calculation?
The subgrade has already been considered when you calculated structural number, because that's something that you have to work with what you got. The subgrade that's there, you have to do something with. Now, you might do a cement treated subgrade layer, but that would be treated more as a sub base. So you can include some structural capacity there. But really what structural number did, when we used that picture nomograph thing or did the calculation to calculate structural number, we've already considered that subgrade.
Okay, and sticking with subgrade, are deep excavations weakening the subgrade like sewer lateral connections to main? And do these excavations reduce the effective life on the road?
Yes and no. Just the fact that you're digging out does not necessarily mean that you've done anything wrong, that you're going to destroy what value you have in the subgrade. However, it all depends on what you put back in its place. If you're doing utility cuts and that type of thing and you don't get that compacted well, it is going to kind of undermine a lot of your structural capacity. So it all stems from how much or how well you compact the material around that pipe and in that area. It's got to be compacted very, very well, or you will see those spots cause problems later on.
Okay, great. That is everything that I have.
All right, and I am going to just kind of blow through this last little section about subdivisions, because a lot of the things here I've already mentioned as we've gone through the slides. But in subdivisions, we think, oh, we don't need that much structure, but we do. So you can see evidence here. Where does the mail truck stop every day? Where does the trash truck stop every week? Those are the places that you'll start to see some issues. Part of that, I think, comes from the fact that when someone builds a subdivision, the developer will come in and put really nice streets. They put in their curb and gutter because they want to sell the lots. They want it to look great. But that is the worst time to build your roadway, because the first thing that's got to happen in there is that we bring in all of the construction equipment and trucks that are hauling, concrete trucks, brick trucks, all the supplies are coming in. And those are the heaviest loads that those pavements are probably ever going to see all at the beginning. So one of the things that I suggest is designing your subdivision streets to have 2 layers of asphalt, either an intermediate course and then later a surface. But if you really want it to be paved during the time that the houses are being built out, leave an option to come back and put the surface on later. And that's kind of something that maybe within the city and the permitting, you have to come up with some rules and things. But your pavements will last so much longer if you can have all of that construction traffic done and out of the way, and then put your nice final surface on. You will have to manage drainage at that point, so maybe some little cuts in that curb, because you'll have that lip, and we do need to maintain drainage. But just think through those types of things and what we've learned about all of the damage that happens from those bigger trucks. So just recapping, first thing is drainage. Second is get an accurate characterization of your subgrade, count your traffic, forecast as best you can, and then we're coming up with a pavement thickness. So that is, I think, pretty much it. So I don't know what I just did. There we go. Hopefully we're back to what we're supposed to be seeing. Anyway, so thank you very much. I appreciate your time. And if you can, there's going to be an evaluation that pops up. I'd love to get some feedback on what you thought about the webinar. So thanks so much. Have a great afternoon.